Okay, now we are going to talk about a detailed explanation regarding the Gauss law. What I am going to do is I will try to build your intuition regarding why Gauss law has to be true. Okay. So, for that I am going to use a very simple analogy regarding flow of water, right. So, let us start. So, suppose this is some weirdly designed room. Okay. I do not know why someone designed this kind of room, maybe to explain the Gauss law. So, this is a weirdly designed room. In that room, there is a flat floor, obviously. Near the walls, there is a gutter or a small channel into which the water could fall and it would go out, okay, to some reservoir or anything, right. So, what we are having is at the center of this room there is a tap, okay, at the center of the room there is a tap through which water will come out from that pipe and enter the room. Two little children, right, have drawn two curves or two shapes on the floor, one with a blue ink and another one with a red ink. Okay, the blue one is a nicely designed rectangle surrounding that tap, but the red one is a weirdly shaped, okay, is a weirdly shaped one, and there is no definite size or shape or anything, right, it is just very random. Okay, so in such a case, I want you to think of what is going to happen when we turn the tap on and we do not put any vessel to hold that water underneath, right. So, the tap is just on and the water is flowing out, so it is going to hit the floor and then it is going to spread out, correct. Okay. So, I am sure you do realize that if in some time, let us say that in some time some 5 liters water comes out from the tap, okay, and enters the sink on any of these sides. Okay, let us assume that in some time 5 liters of water comes out from the tap like a fountain or maybe just falling on the floor. In some way it is coming out from the pipe through the tap and now it is on the floor of the room. Okay. So, in that case 5 liter water has come out from the tap and it has flown into the sink in any direction. We do not know exactly how much has flown in which direction, that is not important, right. So, my question is, if you would sit there and somehow you could measure how much water crosses, how much amount of water crosses the blue line, okay, painted on the floor in the form of a rectangle, or the red line or the red curve painted on the floor again, right. The question is, how much water would have crossed the blue or the red lines in any direction whatsoever. You just have to take total, right. Think about it carefully. I am saying that 5 liters of water has come out from the source and it has been spilled on the floor and it has now moved outside towards the gutters or the sink in any direction and it has gone into the sink. Question is, how much water would have flown through either of these blue lines or through the red curves? What's your answer? What do you think? It has to be 5 liters, correct? Because if 5 liter water has to go from the tap through to the sink, it must cross the red or the blue lines, correct? Now think about this crosses or passes through. So that's exactly what is flux, right? And do you realize that both of these are closed curves in the sense of a floor? Because if water must flow out from the tap in any direction, it definitely has to cross that curve, right? So the same thing happens with electric field lines in 3D, right? Again, do you realize that the area or the size of the curve, that doesn't matter, right? It's possible that I can take one little blue circle here, and if I would ask you how much water would have crossed that blue circle in that time, right? Then the answer would still be 5 liters, correct? So this is what is the idea behind Gauss law, right? You should understand that a point charge, right? Let's say a positive point charge over here, it actually behaves like a source of electric field lines, that is. What I mean to say is that electric field lines, they come out as if this is a tap, a source, right? Correct? Okay. Agreed? Right? So what happens is that if you would imagine a surface that encloses this one, of any shape, doesn't have to be a sphere, doesn't have to be a sphere. That surface could be of any shape, right? It could also be a cube, like I did earlier, right? So it doesn't really matter what is the shape. It should just enclose that charge. That's it. So in that case, the field lines for that charge must pass through that surface, right? And that obviously, how much field or how many field lines pass through that surface depends on what's this charge Q. If it's more, the electric field is stronger, we have more field lines, and then that means there is more flux passing through that. It's again similar over here. Instead of this tap, let's say I replace it by another tap, right? Tap 2, okay, which is having more capacity. So in some given time, it's going to throw out more water. So what we'll have is more water will pass through these red or blue curves. Same idea over there. If instead of charge Q, you replace it by something which is having a bigger magnitude of charge, 2Q. In that case, there is going to be more electric field and more field lines and more flux passing through the closed surface. Alright, so that is why I hope it is quite clear that the flux for a closed surface should be dependent on the total charge inside it, right? See, the word total is also important. What if I had put one more tap over here? What if I put one more tap over there and turn it on? Then obviously there is going to be more water flowing out through these curves in the same time, right? So because this tap 3 is enclosed by the blue rectangle and the red curve, so the amount of water flowing out through that curve, right, either the blue rectangle or the red curve, is going to be much more, right? So what happens is, if there are more number of charges, right, let's say over here there is one more charge, so the electric field is going to be even stronger and there are more field lines coming out from this, right? Obviously the shape of the field lines will change, I agree with that, but I'm sure you do realize that now there is more, it's just like there is more water coming out, okay, from inside this, and that's why more water must flow out, right? So because of that, the flux is going to increase, just like that, more charge, more stronger field and more number of field lines coming out, so the flux will increase, and that's why the total is important. On the other hand, if you are going to put a negative charge, then the negative charge actually takes in the electric field lines, right? Because I hope you do remember that the electric field lines come out from positive charge but go inside a negative charge. So because of that, what happens is, it's like it's absorbing or taking in some of the electric field. So in that case, due to the positive charge, let's say we have 50 flux going outside but 10 flux coming inside, right? Okay, 50 flux going outside and 10 flux coming inside. So the net flux going outside is only going to be 50 minus 10, that is 40. So this is what negative charges do, right? See, positive charges are like source. From those charges, the electric field comes out. But negative charges, they are like sink. Sink, that is, the water goes into that sink, right? The water goes into that sink. I want you to understand this by a slightly modified version of the same example. Think about, again, let's go back to the original case. Let's say there was only one tap, Okay, tap 1. Throwing 5 liter water in some time, right? So that is going out. But now suppose I create a tiny sinkhole over here. Let's say we create a tiny sinkhole over there inside this. So this is a sinkhole. What do you think will happen? Some of the water will end up inside this sink as well. Agreed? Right? Correct? So what's going to happen is, because of this sinkhole, the amount of water flowing through the curve will decrease. Right? Because some of the water will go into that sinkhole. Exactly the same case with the charges. Right? If I've got a positive charge, it's going to throw out the electric field or the field lines. But if you've got a negative charge, it's going to take in the field lines, right? So that's why the net is going to decrease. Only, it's possible that with only the positive charge, the flux would have been 50. But along with that positive charge, suppose we put a negative charge, and because of that, there's some reduction, because the electric field lines for a negative charge come in. It's like a sink, okay? So that's why the electric flux depends on not just a single charge enclosed, but rather the total charge enclosed. So if there are more positive charges inside, there are going to be more field lines going out and more the flux. But instead of that, if there is some negative charge, then the field lines are going to come in, and that's like opposite, right? So 50 outside, 10 inside makes it 40 net, right? So because of the negative charges, the flux is going to decrease, right? So remember that the flux indicates the number of field lines passing through the surface, right? And here we are considering outside as positive and inside as negative. That is the convention, right? Let me write that here very clearly. So by convention, we take flux going outside the closed surface as positive, and inside the closed surface, or going inwards, actually, let me just write inwards, going inwards the closed surface, outwards and inwards, right? So flux going outwards as positive, and the flux going inwards the closed surface as negative, right? Okay, along with this, you should remember that when we take area vector for closed surface, see, with open surfaces, I do remember that there is a possibility of confusion, isn't it? Suppose there is a rectangle like this, then you take area vector in this direction or the opposite one, right? Because both of these are normal to the surface, right? Okay, so which one shall you take? Well, here by using this convention that the outward flux is taken as positive and the inward flux is taken as negative, we can actually get rid of this confusion. Let me tell you how. If you take the area vector as outwards from a closed surface, right? Again, like I said, because we are taking outwards positive, we should take area vector outwards as the correct one, because, have a look, if you take it this way, outwards, what happens is, suppose this is some electric field outwards, right, outwards from this closed surface. So in that case, the angle between S and E vectors, that is area vector and electric field vector, theta will be acute, right? Theta is acute if electric field is outwards. I'm sure you do realize this, right? So right now we are talking about how to take the area vector for a closed surface, right? And I'm saying that if you take the area vector outwards, then what happens is theta will be acute if electric field is also outwards. And in such a case, this convention gets followed, right? I hope you realize why. Because if theta is less than 90, that means cos theta is positive. If cos theta is positive, the flux is also positive, because roughly speaking, for a small surface or for a small part, it is going to be E ds cos theta, right? So what I mean to say is, as long as theta is less than 90 or acute, the flux is positive, and that's what the convention is if the electric field is outwards, right? So to sum it up, let me tell you that according to this convention, the area vector for a closed surface must be taken perpendicular to the surface, in outward direction. Okay, you don't take it in inward direction, you take it perpendicular to the surface but in outward direction. Alright, so that is the use of the convention, right? So if you follow this convention, the Gauss law is perfectly valid, right? Okay, so I'm going to sum it up about the Gauss law, right? We have finished the discussion. Let's summarize what we have learned about the Gauss law. Number 1, you can use the Gauss law only for closed surface, right? Not for open. Okay, the Gauss law is valid only for closed surface, not for an open surface. Second, the surface may be imaginary. No problem, right? The surface may be imaginary. So I am saying imaginary surface is allowed. That is, you could imagine a surface on your own. So that means you can actually take any shape, right? So that brings me to the third point. Shape of the surface is not important, right? That is, you can use the Gauss law for surface of any shape. Number 4, the formula itself, right? This itself is the formula. So sigma q enclosed divided by epsilon 0 gives you the electric flux for closed surface, right? Again, what kind of closed surface? That we have already defined in 1, 2 and 3. Next, we take the outward flux or outward electric field, we consider that flux as positive, right? And the inward flux obviously as negative, right? Opposite of that, right? Okay, so when you want to find the net flux, you have to do outward minus inward. The next thing is about this area vector. We define the area vector such that it is area vector is normal or perpendicular and in outward direction. Okay, for a closed surface again, and outwards from the closed surface, right? So these are the points that you should remember when you want to use the Gauss law, right? Again, to clarify this, what is meaning of sigma q enclosed? It means you just have to add all the charges present inside or trapped inside that closed surface. Remember, never use it for open. Okay, so that's the main feature of the Gauss law. Alright, so that's it about the Gauss law. I hope you'll be able to remember all these properties because they're extremely useful when we want to do calculations.